In this week, we will discuss the evaluation method for the classification and prediction. In the previous several classes, we discussed several steps for the data mining. Firstly, you need to obtain data and clean the data, remove the noise, reduce the dimension of the data. Then you can make a partition to the data, obtain a partitional data sets, validation data sets, and test data sets. Then we can apply different methods for the evaluation and classification prediction. And we also need to compare the different methods. Then we make a decision which one is better or the best one. Actually, the comparison between the classification and the prediction is about the value of the output. If the value output is about it's just only categorical value, only several possible value, this will be the classification. For the value is a numerical value with decimal points, that will be the prediction. So here we will evaluate the output and the outcome of the interest can be the numerical value. It can be one member in a class. We can also say we have several possible value inside one class. So we can make a decision which one class for this analysis belong to. Actually, we can make one conversion from the numerical value to the class. We can use the approximation method using the floor function or the ceiling function. If the value larger than 0.5, then will be the higher number. If lower than 0.5, then will be a lower number. Okay, here's the code for the Python. Okay, use these packages. You use the math. Math is for the mathematical function, like the log function, exponential function, cosine, sine function, etc. Panda for the display and also access to the database, like the Excel file. Okay, sklearn. This one model selection will be about how to split the data into different sets, partition, validation set, and test set. This linear model is for the linear regression. The metric is for the evaluation, how to make a score for the accuracy, how to obtain the ROC value for the curve. And the next one, matplotlib.pylab, is for the display. You can compare the display using pandas and also using matplotlib. You can make a comparison between two methods. We discussed this in the previous class. You can go back to check the lecture. Okay, next is a DMBA. DMBA is a data mining package, DM data mining. This we will use regression summary. So it will return the summary report according to the metric analysis results about the mean error, square root error, and the classification summary. We can also obtain a lift chart and a Gantt chart. Okay, the prediction is one numerical value. Yeah, so just now we said already. Classification is just one categorical value. You can also say it's one integer value. So this measuring method for the predictive error is about how well the model predicts the new data, not how well it fits the data it was trained with. So it's not for the approximation, it's for the prediction. Yeah, that was the difference. The fits just make approximation with the known data. Yeah, this is for the training data. We try to find the most probable approximation with the lowest error. Yeah, then we can determine the questions for the methods. This prediction is used for the validation data or test data. It's for the prediction. And we will not care about the how fits the original data, but we can compare the accuracy for the prediction and to see how much difference between the predicted value with the original value. So we will compare the actual value y and the predicted value y. And this y will be y star. Here there are several measures. Actually, we discussed MAE is mean absolute error. We can also say it's one deviation. Next one is average error. MAP is mean absolute percentage error. Yeah, that's RMSE, root mean. Okay. Last one is total SSE. Yeah, total sum of the squared errors. Actually, mostly we will care about the MAE. Yeah, and also the average error. Yeah, RMSE, root mean squared error. Okay, this one is for the lift chart. We can use this lift chart to analyze the prediction error. Okay, in this lift chart, the y-axis is a cumulative value of numeric target variable. Okay, x-axis is a cumulative number of the cases. Yeah, we can also make one percentage display for the x-axis. Yeah, we just divide the cumulative number for the cases by the maximum number of cases. Yeah, so the y-axis will be one percentage number from left to right in order of the predicted value. So at everyone x-axis, that's one point with a y value. That is about the average numeric value per record. So here is the one example for the lift chart. This lift chart for the validation data using the trained model. There are two curves. Okay, the bottom curve is a cumulative spending using average. Yeah, this actually is a linear increase. And this will be the ideal situation. The more cases, the cumulative value will be increased linearly. But actually, the distribution for the prediction performance will be one curve like the top one. That's a cumulative spending when sorted using predicted values. And we can see the prediction performance, the best performance will be at the middle position because it changes most quickly with a higher deviation with the ideal situation. Okay, next one is for the accuracy for the classification. The classification has arrow. We can say this arrow is from the misclassification. When we classify the output to another one class, but actually it belongs to one class. Yeah, so there's a deviation between the classification. So we can obtain the error rate for the misclassification results. Will be the percentage of the misclassified records over the total number of records in the validation data. So this is the concept for the error rate. Okay, next is the naive rule. Okay, this rule is to classify all records as belonging to the most prevalent class. Yeah, so this naive rule will be discussed in more detail in the next several classes. Yeah, we will use the possibility distribution inside the dataset. Yeah, we will obtain several possibility. Then we can derive the analysis results. And we will use two rules and compare the difference between the two rules. Okay, next is the separation of the records. Okay, there are two groups of records, high separation of the records, which means using the predictor variables will attain low error. Okay, the low separation records, which means using predictor variable does not improve much on naive rule. Actually, the predictor variable is for the input variables. These high separation records then mean the records can be classified into different groups clearly at ease. If the records are in a small area, in a small range, it's very difficult to separate them. Yeah. So even though you use the predictor variable, you can't make better improvement using this naive rule. Yeah, that means this naive rule can provide better results if the group can be classified into different classes clearly. And because these different groups have different distribution pattern, so we can make the classification at ease. Yeah, so this is what that means. The performance depends on the data distribution. Yeah, we can use the possibility to make a classification. Here's the one confusion matrix. This is for one example with 3,000 cases. In this table, on the top is the active classes. On the left is the predicted classes. So this class has two possible values, 0 or 1. Yes or no. Yes is 1, no is 0. If the active class is 0, but we also classified as 1, 0, so the predicted value is 0. For this case, there are 2,689 cases. Yeah. The next one, possible accuracy results. The active class is 1. The predicted class is also 1. For this one, 201 cases. There are two possible wrong classification. The active value is 1, but we predict at 0. For this, there are 85 cases. Yeah, if the active class is 0, but we predict with 1, we have 25 cases. So the correctly classified as 1 is 201. Correctly classified as 0 will be 2,689. Then there are two groups of errors. Incorrectly classification will be 89, 85, and 25. Yeah. So we can obtain several values. One is the overall error rate. That would be all the wrong classification cases divided by the total number of cases. Yeah. So here is the 3.67%. Okay, the accuracy will be 1 minus the error rate, the overall error rate. So this one has a wrong expression. So this should be divided by this will be correctly classified cases divided by total number of cases. So this will be 96%. We can also use this example to evaluate the example with multiple classes. Here only 2 classes. You can make classes with the value 0, 1, 2, 3, 4. So we can obtain the error rate and accuracy using this similar definition. The error rate will be the sum of the misclassified record divided by total records. The error rate will be this. The accuracy will be 1 minus this error rate. Okay, next one is a cutoff for classification. Okay, there are 2 steps in the data mining classification process. For every one record, we can compute the probability of belonging to the class. For this example, is 1. Then compare to the cutoff value and classify accordingly. So in the first step, we will obtain the numerical value. Yeah, so we say it's one prediction. The next step will make a cutoff to obtain the classes. Okay, for the default cutoff value is 0.5. If the value larger than or equal to 0.5, then we classify it as 1. If less than 0.5, the class we can classify it as 0. And we can adjust this cutoff value to different values, so we can obtain the performance. at a different requirement, because you want to make a lower value for the threshold. The more cases will be the class 1. If you increase this threshold value, there'll be more classes will be classified as 0. Yeah. So this is depend on your interest. Yeah. So we want to obtain more 1, more 0. So you can use this adjustment. Okay, here the example. We have the classification results, predict probability of being an owner. The actual value will be this first one column. The predict probability value is one float point number from 0 to 1. We can use the threshold value for the cutoff is 0.5. Then this will be the owner because it's larger than 0.5, and this also be 1. Yeah, all the cases will be 1. For this one, I think they say the non-owner will be the actual value. Yeah, so this classification is not accurate. The last one also not accurate, but this one predicted value is low, 0.62. So actually we have two wrong classification. The others are correct. Okay, on the right side, 0.5 is owner is yes. This 0.47 is less than 0.5, so it's non-owner. So this is a correct classification. Okay, let's also correct. Owner, this is wrong because 0.2 less than 0.5, so it should be non-owner. But here is actually is the owner. This is wrong. Okay, the others are less than 0.5. They are all non-owners. Yeah. So this was this data. Okay, the previous results. Okay, this the next one case, we use a cutoff value 0.8. Okay, so the threshold position will be at here. Yeah, at here. So we can see there are 7 cases are correctly classified with 1. Yeah, they are all correctly classified. So the top 7 are classified as 1. Yeah. In the previous example, we used the cutoff of 0.5. The 0.5 is here. Yeah. So all the cases less than 0.5 will be classified. It will be predicted as 1. Yeah, as owner. Less than 0.5 will be predicted as non-owner. Yeah. So we have 2 groups for prediction. Okay. Then we continue to obtain the analysis results. So we can use the Python code to make this calculation of the confusion matrix. Okay, we define the predicted to be owner if the P, the probability is less than 0.5. S will be non-owner for P in a owner df dot probability. Yeah, we can create the predicted matrix from the probability value according to the threshold value 0.5. Then we can call the function classification summary by calling the owner df dot class, and also use the predicted definition. They predicted the threshold value 0.5 cutoff value, and also the class name. One is non-owner, the other one is the owner. Okay. Then we can obtain the results for the confusion matrix. So the results show that the correctly classified non-owner is 10 cases. For owner, it's 11 cases. For the wrong classification, the actual value not owner, actually we predict as owner will be 2 cases. Yeah. For the actual value owner, but predict as one not owner, only has 1 case. Yeah. So according to this one table, this table can be obtained from this one probability results. We said that 0.5 will be this one page. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. So it will be okay. No, that's the same. So it will be 13. And this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 13 cases are predict one, predict owner. 11 are predicted non-owner. For the predict value, the correctly classified as owner will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 are correctly classified, but 2 are wrongly classified. So will be this one. So will be so this a little okay. Will be here. The predicted as owner are totally 13. 11 are correctly predicted, but 2 are wrong predicted. So for the predicted results with the non-owner will be this. We will find there's one wrong predicted, but the other 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The other 10 are correctly classified. 1 is wrong, 10 are correct. So we have this one is wrong, correct classified, but 10 is wrong. 10 is correctly classified, but 1 is wrong classified. So we obtain this matrix. You can also try other cutoff value, such as this 0.25. So you can obtain these results. If you have 0.75, you have this other one matrix. We can verify this. We just use this one, 0.5. 0.25. Actually, this one, these are for 0.8. 0.25, I think we can insert one bar. Just use the same. We can copy paste 0.25. 25 will be here. The top one will be top one is 33, so larger than 25. The next one is 25, 21, the less than 25. So the threshold was between these two cases. So then we can count the correctly classified is one owner, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 are correctly classified as owner, but 1, 2, 3, 4 are wrong classified as non-owner. So we have the 4 is here, is wrong classified. 11 is correct classified. So for the next one, so the 1 is wrong classified as non-owner, but 1, 2, 3, 4, 5, 6, 7, 8. 8 cases are correctly classified non-owner. So we have the 8 here, 1 is on the bottom. You can try this method to obtain the other confusion matrix according to different cutoff. Okay, next is the example. Okay, Here we have the definition for the importance of the class. If one class is very important, that means more cases will be classified to it. So we can use this method to analyze the test fraud, credit default, response to the promotional offer, etc. So we can use this confusion matrix to analyze the results and calculate the accuracy and error rate. Actually, according to this one confusion matrix, you can obtain the accuracy. Accuracy will be the credit classes number of the records divided by total number of the cases. Here we say accuracy is 79%. We can also use this confusion matrix to compare the classification methods. Which one method has higher accuracy according to using the same cutoff value. So we can use this method to evaluate the algorithms. We can also use other measures to evaluate the accuracy. Here we have C1, which is the important class. We can define the sensitivity. We can also call this sensitivity recall. So this is a percentage of the class C1 correctly classified. So this will be the same as almost the same as accuracy. But this is used for many classes. This is just C1. You can also use C2, C3, etc. Specificity is a percentage of the class C0 correctly classified. And the next one, definition precision, the number of the predicted C1 that are actually C1, C1s. It's a precision. Here we have the ROC curve. This very similar to the lift chart. ROC curve. You can see the horizontal direction is a percentage. The false positive rate. Specificity. The vertical direction is a positive rate, which is the sensitivity. So we can make the ROC curve to describe the relationship between the sensitivity and the 1 minus specificity. Actually, we can use the software to make this ROC plot by calling the package function. Actually, in the slide, we know that we call this package at the beginning of the Python. We have the lift chart and the Gantt chart to obtain these two charts. And also we have the ROC curve function, lift chart ROC curve. So we can use these two functions to obtain the two figures. Okay, ROC is an abbreviation for the words receiver operating characteristics. We can use this to measure the effectiveness in identifying enemy aircraft, such as distinguishing the signal from the noise. Just like this one curve, the height deviation will show that the best performance will be at this segment. So the best performance, the percentage will be 0.2. To quickly reach the saturation at about 0.3. So the best performance range will be around 0.2, 0.3. If you use a higher number of the cases, it does not change the performance, or just change very small. the big changement of the performance will be at the beginning. Yeah, so you can use a small amount of the asset or investment to obtain the best results. Okay, this is the example for the ROC. We can use this ROC to measure a model's effectiveness in separating the wheat from the chaff. Yeah. Lift or gains is a similar metric, but measuring how much does the model improve on random chance in finding the class of interest. We will discuss this in the future with more examples in a different algorithm. Yeah. This ROC and the lift chart are used frequently in evaluating the performance of the choice of the parameters. Okay, the lift is also termed as a gains, just like this one slide. You know, the ROC is one way to evaluate the performance for the prediction, and we can use the lift to measure we can obtain this lift chart from the ROC, yeah, using the percentage along the horizontal direction. Yeah, we use the percentage for the lift chart. For the percentage for the ROC, but the number of cases for the lift. Yeah. Okay, here we use this lift chart to evaluate how well a model identifies the most important classes. Okay, this lift chart and these are charts actually to compare the performance of the data mining model to no model but pick randomly. Yeah, using these two charts, we can measure the ability of data mining model to identify important class relative to the average prevalence of the class. So actually from, okay, we will go back. Yeah, we have chart in the next two slides. We'll discuss this in more detail. The charts give implicit assessment of results over a large number of cutoffs. Okay, the sequence to use this lift and desire charts. Firstly, we need to sort records by predicted probability of the belonging to the important classes. Yeah, here is one, class 1. Okay, then we move down the list, noting active class. Then we can compare the number of active ones to the number of ones you would expect with a no model. In the lift chart, we can compare the step function to straight line. A straight line will be diagonal direction, increase linearly. In the desire chart, we can compare to the ratio of 1. This ratio 1 will be the one horizontal line. Then here is the results. This is the lift chart, or you can call this as the gain chart. So horizontal direction will be the number of the record, number of cases. Yeah, vertical direction will be cumulative gains. Yeah, from this one plot, the lift chart plot will be the blue color. Yeah, the ideal line is one diagonal direction. Yeah, from the 0 to here the is 24, 12. Yeah, about that. Yeah, from this one, you can see at the position with the time records, you can see there are 9 owners. Yeah, in the y-axis have been correctly identified. Yeah, after you reach the about 16 records, yeah, all the okay, seem like it's the best final results will be around 16 records. Yeah, when you increase the number of records, the results, the gains will not increase anymore. Okay, Python code is here. We firstly obtain the data from the SF file by calling the pandas read CSV. Yeah, we already have this already. Then we call the sort values by the field PROB. Ascending is a false ascending. So it's a descending. Yeah, so we can realize the sorting on the original data on the field probe. Okay, then we call the function gains chart, okay, using the ATU value and the fixed size is set at 4 times 4. Yeah, 4 inch times 4 inch. Yeah, so we have the 3-line code to obtain this Gantt chart or lift chart plot. Okay, this next one is the decile chart. The decile chart a little is different with the lift chart. Yeah. Lift chart is an increased accumulative value for the gains. The more records, the more number of the correctly classified examples. And this decile chart horizontal direction is a percentage tile. As we make a bin category, yeah, 10, 20 until 100. Yeah, from this one table, the case selected as random will be the value at 1. Yeah, so actually you can get this from the decile. Decile chart will compare to the ratio 1. The case of 1, that means the model is chosen as random. Yeah, we choose the cases randomly, and to see whether the predicted results is accurate or not. So the default value is 1, but here we have the lift value is 2. Yeah, the 10% has the accuracy with 2 times than the normal chosen as random. 20% also good. For the 50% is the same as the chosen at random. Yeah, and the 60% will be worse than the random case. So this was the basic meaning. We will be familiar with this usage using the examples. Okay, here provided the method to compute the lift chart. Yeah, we use the model's output, sort records from most likely to least likely members of the important class. Then we can compute the lift, accumulate the correctly classified important class records. That actually is along the y-axis. Then compare to the number of total records. Yeah, this is correspond to the x-axis. Yeah, actually, from the previous 2 figures, the lift chart and the decile chart, we can see the difference. The 2 charts both can be used to move down the analysis possibility from the most probability value 1 to approaching the 0. The decile chart use the bin value along the horizontal direction. Yeah, we have to make chunks of the data by column display. Just use this column display. So y-axis show the ratio of decile means to overall mean. Okay, lift chart show the continuous cumulative results. Yeah, so actually it's just one curve. Yeah, it shows the number of important class records identified. Yeah, So it will be accumulated results along the y-axis. But the decile chart will show the ratio of the decile mean to the overall mean. Yeah, for the random chosen method, the value will be 1. Yeah, actually we have this. This is ratio value from 0 to 2. Okay, 1 will be the random case. And we will compare this line, this one value, to see the method is better or worse. Yeah, from the previous slides, we can see the gain chart, RC chart can have similar appearance. They can be used to, both of them can be used to analyze the analysis accuracy and see what's the pattern for the distribution for the analysis. And the RC curve provide a widely used single metric and visual to assess models' ability to separate classes overall. And the lift chart is an intuitive measure of model performance at different cutoffs, but no overall metric. So the difference between the two methods. Okay, now we discuss the asymmetry cost. The first one is the misclassification cost. We can evaluate the misclassification cost for different methods. And maybe one cost for one method is higher than the other one method. If the cost is too high, we may reject that method. Here the example. For the response to promotional offer. Suppose that we send one offer to 1,000 people, but only 1% average response rate. That means 99% of the people didn't make any response. Okay, one is show that there's one response, 0 non-response. Okay, here we have the naive rule. This has the definition to classify everyone as 0. Yeah. So that means it assumes everyone will not respond. The default choice value is non-response. Then the error rate will be 1%. Yeah, because 1% has response. This naive rule is care about the class non-response. So the wrong rate is 1%. Yeah, this is good. Actually, it's good. Okay, using the data mining, we can correctly clarify 8.1. For the data mining method, 8.1 correctly classified, and we have misclassification 20 0 as 1 and 2 1 as 0. So totally the misclassification 20 plus 2 will be 22. Yeah, so we can have this confusion matrix from the previous slides analysis. Actually, it's not easy to obtain the confusion matrix from this page description. This is not that easy. So you have to detail analysis on this. Yeah, here it says misclassification 0 as 1. So we have the 20. Misclassification 0, the actual value is 0, but we classify as 1. So here is 20. And the next one, 2, 1 as 0. That means the actual value is 1, but predicted as 0. Yeah. So for this, there are two cases. So it's 2, 1 is predicted as 0. So here we have these two values. And we have the error rate. The error rate is 1%. Error rate 1%. That means one is the average response rate. But total is 1,000. 1% average response rate. That means about 10 cases have the responses. 10 responses. So that means there are 10 actual response. Actual 10. Here that means actual is 1. The total is 10. So we know it's 2 on the top, so we have the 8 on the bottom. Okay, so total number is 10 on the column 81. So this is from the condition 1% average response rate. And according to this condition, 1,000 total people. So we can derive this number. It's 970. Yeah, because we know these other three numbers, so we can derive the credit classified 0 to 0, so be 970. So we have the error rate. Error rate will be this two number, 220, to divide the total number of the cases. Total number will be 1,000. Yeah. So this method has an error rate 2.2%. For the naive rule is has the error rate 1%. Yeah, so we have the better performance for the data mining method. So this naive rule is just assume one default class to be one major important class, just 0. For the case, the error rate is 1%. And from here, the computer matrix will show the prediction as row, attitude, and column. Here the cost and the benefits. So we can define the profit for one with a $10. The cost sending one offer is $1. So then we can calculate total cost for one project. And because we have two methods, one is the naive method, the other one is the data mining method. For the naive method, everyone is assumed to be 0. Yeah, just now, as in the previous slide, all are classified with 0. So no offer are sent. Yeah, because it assumes no response. No response is 0. And non-response. Okay, for this naive rule, no response obtained and also no offer are sent. So there are no cost, no profit. Okay, for the data mining predictions, 28 offers are sent. Actually, from the previous slide, the department sent out 1,000 offers totally, but they received 1% for the response. 99 is non-response. And this data mining method can predict it correctly 99%. Oh, sorry, it's 97.8% for the accuracy. The error rate is 2.2%. But for the naive methods, the error rate is 1%. And it just assumes everyone will not respond. Yeah, from this computer matrix, the 8 response with profit, each one is $10. But 20 fail to respond, as the cost is $1 each. And we also have 972 receiving nothing for this group. No cost, no profit. So we can have the profit matrix according to the computer matrix and the definition of the profit and the cost. So have this profit matrix because the 972 without cost, without the profit. So we have the 0 in the first row. And the bottom row for the 20 case, we have the cost $1. So we have $20 for that one. For the 8 case, profit $10. So total is $80 here. Okay, here is for the lift chart. Yeah, also we can use the lift chart to analyze the cut-off, determine the best cut-off to realize the maximum profit. And the usage of the cost and the profit or benefits does not change the classification results, but it is useful to estimate the best cut-off value. Actually, it's not always too easy to estimate the cost and the benefits for the classification. Yeah, it's a good habit to obtain the detailed information for the cost and the benefits so that we can realize the best classification. Okay, one good practical substitution for the individual cost is the ratio of misclassification cost. Okay, next is the minimizing the cost ratio. So here we have the two values, Q1 and Q0. Q1 is the cost of misclassing ATU1, Q0 is of the cost misclassify ATU0. That will make the ratio, which is called the cost ratio, Q1 divided by Q0. We can minimize this cost ratio to obtain the best performance. So minimizing the cost ratio. So we have the Q1 and Q2. The cost of misclassifying ATU1, misclassify ATU0 for Q0. So the for the opportunity costs, it's better to convert everything to cost. So we're only interested into the costs because we want to reduce the number of costs. It's not a good idea to make the mixture of the costs and the benefits, because it's hard to say one constant benefits. The benefit can be changed during the long period. Yeah, maybe it's cheaper. In the future, maybe more expensive. Yeah, but we usually care about the current cost, the benefits. We mostly about the cost. Yeah, cost is most important. We will determine whether the plan is possible or not. So the referring only to cost allows greater applicability. Because the cost is too high, it's not possible to continue this project. So this is a condition for the possibility to apply that project. So that's why we are focusing on the cost instead of benefits. Here we have the cost matrix, $8, $20, also $20. And we also have the original confusion matrix here. Actually, we can realize the conversion according to the definition of the cost for everyone case for the individual situation. So here we have the definition of the profit. Y is $10. The cost of sending out the offer is $1. So we have this conversion from the cost matrix to the confusion matrix, or you can say it can be inverse. Okay, the previous example just for the case only two classes, 0 or 1. We can also to confusion matrix for the multiple classes. For the case M classes, actually we discussed before, we can create the categorical variables from one numerical value M. Yeah. We can make the M class, M minus 1 classes. For this one case, this M classes can create the confusion matrix M times M. Yeah, M column, M rows. Okay, only the elements along the diagonal direction has a correct classification. The other will be misclassification. So the total number of misclassification will be M times M minus 1 misclassification. M row and M column. Okay, this is for the case adding the cost and the benefits to the lift chart. The method will be from the sorting records in descending probability of success. Descending probability of success sorting. Then for each one case, we record the cost or benefit of the actual outcome, and also record the cumulative cost and the benefits, then plot the records. X-axis is the index number, Y-axis is the cumulative cost or benefits. We also draw one reference line from original to the value Y in is the total net benefit. Actually, in this class, we will not care much about the cost or benefits. Yeah, we will just focus on the lift chart and also the desired chart. From the analysis using the cost and benefits, the curve may become to negative value. The total net benefits from all cases is negative. Reference line may have negative slope. The goal is to use cutoff to select a point where the net benefits is at a maximum. This will be careful the usage of the lift chart to find the best position to obtain the maximum performance. Maximum benefits. Okay, here's the example. This plot shows that the reference line has a negative slope, and the lift chart has one curve, and we can obtain the maximum value at this position at about 3,000. At this position have the best performance. So this was the conclusion. And the more cases, the benefits will be lower, and the cost will be higher. So that we have the balance between the number of the cases and the benefit. So we can make one small number of cases to reach. Okay, next is the discussion for the oversampling and asymmetric costs. For the cases with the rare cases, asymmetric cost or benefits typically go hand in hand with the presence of rare but important class. So this is for the case with a rare but important class. And we can use this method to the projects, responder to mailing, date defaulter, and someone who committed fraud. So we just find one rare case, rare classes, but we think they are important. We can make an oversample for the rare cases to improve the number of the rare cases so that they will become important. So we can oversample rare cases to give model more information to work with. Usually we will use 50% Y and 50% 0 for the training. If the cases of 0 is very small, we try to increase the number of the case of 0 to be 50%. And this is used for the training set. Okay, this is the example for this oversampling. This shows the optimal classification in a 3 scenario. First one, assuming the equal cost of misclassification. Next one is assuming misclassification O is 5 times the cost of misclassify X. The third case, the oversampling scheme allowing data mining method to incorporate asymmetry costs. Here we have the example for the cases. Okay, we have the cross point and a circle point here. When we apply one classification threshold value here, so on the left side will be classified as S, right side will be classified as 0. So the circle will and X are for the original A2 classification. The predicted results will be applying this cutoff value, cutoff line. So on the right side will be correctly classified with the O. The left side, only one O is wrong classified, the other are correctly classified. So from here, we have the new cutoff value, horizontal direction. Beyond this line will be classified O. Below this line will be classified as S. All the cases below this line are correctly classified, but beyond this curve, 50% are correctly classified, 50% is wrong classified. From this, we can see that the misclassified O, all the O is correctly classified for this case. Then we can define the cost for the misclassification, O or X. Here we'll assign the unequal costs for the misclassification. The previous one, we have the equal cost for the misclassification. The cost for the misclassification of the O, just 1. Okay, this one is an example. By applying the 5 times cost, so it's not convenient to see in this way. I just put the figure in 1, so it'll be easy for you to understand. Okay, so we have the weighting for the O point. Will be applied 5 times for the weighting. Now we can calculate the number of the cost for the classification results. For this case, the cases of the correctly classified to be O is 5 times of the wrong classification to be O. So it's easy to identify this. Okay, here's the procedure to the oversampling of the records. We can separate the responders, okay, rare case, from the non-responders because it's a very small number of cases. Randomly assign half the responders to the training sample plus equal number of non-responders. Yeah. So we make sure it's 50% for the responders, 50% non-responders. Remaining responders go to validation sample. Yeah. Then add a non-responder to validate data set to maintain original ratio of responder to non-responders. Yeah. Randomly take test set from validation if necessary. Actually, we just focus on the two data sets, the training data and the validation data. Yeah, just follow the two principles. Yeah, the responders should be the rare cases, important class should be amplified by adding more points, just like this one, add more points in the samples. And we try to make sure 50% for the rare case. The other 50% will be from the other cases. Yeah. Okay, here's the classification using tri-edge. This is the case for the situation to consider a gray area in making classification decision. Yeah, instead of just the classify 0 or 1, we may classify it with the 3 possible choices, C0, C1, and count C. So the third category might receive special human review. Yeah, we will investigate how many in the middle. Okay, here will be the conclusion of this lecture. So we can go to the source code of the example. So we can go to the details to learn how to create the ROC curve, lift chart, and the decile chart, and how to apply the cost and benefits to the data. So we can open the Jupyter. You can go to the command line Jupyter. Notebook. You can upload your notebook of this one lecture. So have the 6 or 5, lecture 5. Upload this. Lecture 5. We can open it. Okay, the first one cell is for the package. We just run all the package. We discussed this already. So cell run this. Then next will be to extract data from the database Toyota Corolla CSV. And so we know that this data is not there. So try load the data. We upload the data. Data is from the zip file. Actually, I already extracted this here. So it's Toyota Corolla here. Then upload this. Then we can run this cell. Yeah, it shows the results for the summary. You can see the code. First one is to read the data. Then we make a reduction of the data. Remove the column, price, ID, model, field type, and the color. We can open the source code as source data. Toyota. So data is here. There are many columns. We try to remove the price column, ID column. ID is make no sense, so we are remove it. And also model is not interesting. And the field type not interesting, and the color. Yeah, color is here. Okay. Then we define the predictors. Predictors from the columns, except the excluded columns. Yeah, we just list all the columns instead of these above chosen columns. Then we define the outcome variable, the price. Outcome will be this one. So the predictor will be the input variable. Yeah, the output will be outcome will be output variable. Yeah, price output variable. Okay, we define these two parameters. Then we define the partition data. We divide into two group data. One is for the predictors. The other one is for the outcome data. Yeah, will be the output data, input data. So we can use these two group data for the training. Yeah. So we have the training test split. Okay, we split these two group of data into validation and test. We use the percentage 40%. 40% is for the validation. Yeah, for the validation. The training will be 60%. Okay, random state is 1. Random state is 1. It's random. Okay, then we call the linear regression. Then use the return results of the training. Training data set, or train X, train Y. We use these two group data, input output data for the training data set to make a fit using the linear regression. So we can obtain the parameters for the linear regression with a best fit. Yeah. Then we call the regression summary. Okay, according to the trained Y original data, will be so it's the actual data. Then will be the predicted data. And we compare these two group data to see the matrix measurements. Is how much error, how much is the standard deviation, how much is the square root error square. Yeah. Okay. Next one would be for the validation set. Yeah. Validation Y, validation predicted validate. Okay. The results will be here. You can see from the training data, the mean error is 0, but the validation is 97. Yeah, because the linear regression try to reduce the mean error to be almost 0. Yeah, because it find the best fit, so the error very small, almost 0. Okay, next will be the to define the data frame. Okay, we have the two new column, residue and a data set. Okay, the residue is assigned with the calculation results trend y, the actual value, minus the predicted value. And we define the dataset as training data. The next one, data frame, we have the data field residue is one difference between the validated, actual validated data and predicted value validated data. Next will be the arrow train appendix function. Using these two predict arrow validation data. Then we plot the make a subplot is 1, 3. It will be one column and one row, but we have 3 figures in one row. Okay, the figure size is 9 times 4, so the width is 9 inch. Vertical is 4 inch. Then we have column. Common. We define the common. The bins is 100. The range is native 6,500 to 6,500. So we define the two parameters. Bins 100. Okay, next we call the histogram using the for the data training data, arrow training data. Okay, using the parameters, the bin 100 and the range of this. And this for the first one is for the figure 0. The next one is for the figure 1 inside this row. Is the row number from 0, 1, 2. Yeah. So for the last one figure will be the box plot. And previously was histogram plot. This box plot will have one. Box plot is using the data of the arrow train, and we combine these arrows together. And we use the dataset to be the labels for individual group data. Yeah, so there are 2 group data using this appendix function. So we make the plot, call one box plot function on the figure 2, axis 2. Yeah, we made a categorical description for the individual data set. Yeah, one is training data validation. Okay, then we set the title for the 3 figure, training, validation, and empty. Then we define the last one figure, the limit in the y-axis. Then will be the plot subtitle. The subtitle will be for all the whole figure, prediction arrows, and make adjustment for this figure. The bottom margin is 0.15, top is 0.85. The white space between the figure is 0.35. Then we enable the display of the figures. I'll call this dot show. Okay, so we have this plot. The previous 2 are histogram. The last one is the box plot. Yeah, so we have the arrow range bar. Yeah. The other point will be the outliers. Yeah, outside this minimum maximum. Okay, here is for the example to calculate the cumulative sum. We use the series function on the predicted value from the validated data. Then we make a sorting on the data. Then we can plot, define the plot with 1, 2. Then have the gain chart plot. So this is a lift plot, lift chart. Using the data from the series. Yeah, so this will be the predicted value from the training data or the validation data. So we can have this plot, the Gantt chart plot. So we can run this code. Okay, run this one. Okay, this. And for this one, we call this. Yeah, it report one warning. Warning is fine, but it says can't display the figure. We're currently using AGG. So I'm not sure what's the reason. Which is the non-GUI backend, so can't show the figure. Yeah, actually, you can copy the code into the Microsoft to see how it displays. Okay, next will be the lift chart. Let's see what's this. Okay, it also can be displayed. So for the convenience, I just copy the code to the Microsoft Visual Studio. So that's why I encourage you to try both software for your convenience. Yeah. So you can define the test. You can define the test. Oh. Then have the test for. So you can copy code here. So copy the first cell. No display found using non-native AGG backend. Yeah, I think maybe it's not a good idea to start the Jupyter from here. You can try the anecdote. Anaconda. Then called Anaconda Navigator. So it's not a good idea to start from the command line. So let's launch the Jupyter from here. And this will be more supported because running from command line will not be supported for some package. So we can have to load again. So we're going to run main. It is report DMBN, not inside. So we have to install this package. We go to the Anaconda, go to environment. We can search maybe that is not convenient. Yeah, we try the Visual Studio will be better. So we copy the source code first. Yeah. I copy all the code here. Make sure you have one indent. I enable all this indent into one function. I enable the first line. Okay, then we can run to see what it is. It should report some errors. Okay, sklearn not installed. Okay, finish. Then try to stop. Then start again. Yeah. It also report error. DMBA not available, so we just install DMBA. Yeah, installed. And stop. And start again. Okay, the file not available. We copy this file to current folder. The Toyota Corolla to the, so we stored here. Paste here. Okay, then we run again. Stop. Start. Yeah, now it's running. Okay, first one figure. And we close it. You can see the next figure. Okay, this is the lift chart. This is a decile chart. Okay, we'll close it. You can see the next one figure. Yeah, so we can get the information for the lift display and also the price for display. Okay, report one error. One file can be found. Owner example. So copy owner example. Owner example. Yeah, for the convenience, I copy all the data here. So this will not be a big problem. I copy all of here. Yeah. So okay, then we start again. Okay. Close it. The second figure, the third figure. So top one is accuracy. The bottom is the overall error. Yeah, this is cutoff value. So we can see which one cutoff value is best. And best will be this here. It can reach the highest accuracy. Could be 0.5 be best one. So that's why we usually choose 0.5 as the cutoff value. Okay, so next one, this is the ROC plot. Okay, this for the lift chart. This for the decile chart. Then we finish. Yeah, you can try the both platform, but V3 will be better for the convenience. You need to make sure how to install the package. Okay, any questions? Yeah, I will provide the assignments of the class so they can have an exercise on the examples. Okay, if you don't have question, we just stop here today. See you next time. Thank you very much.